Hello everybody and welcome back to another video by Funland Tutorials. In today's video we are going to be talking about a very basic statistical concept which will actually develop into much more complicated concepts in the near future. So this is a pretty long concept and cannot be explained in just a couple of videos, so we will be breaking it down into many such videos and we'll be sharing it as a series of videos where we'll be discussing a concept called correlation analysis. So this correlation analysis essentially is the backbone of other topics in econometrics and statistics, such as regression analysis and basically model building. So in economics we have a lot of model building, and that follows from regression analysis, and correlation analysis is one of the fundamental pillars of the concept of regression analysis. Now before the way I learned this through diagrammatic representation, how the data was initially interpreted and how its behavior and nature is understood from the way in which it appears in graphs. So what we'll be doing is we'll just first start with what the word actually tells us. So if you look at the word correlation, the word can be divided into two parts. So there's this co and then there's relation. So it's correlation. Now when you think about co, you have coordination. So that's coordination between two individuals or between two systems. You have cooperation between again two individuals. So here this correlation is actually talking about the relationship between two variables. Obviously these two variables have to be able to be represented quantitatively, so you have to have quantitative variables, and they cannot be just qualitative variables that cannot be represented in a graph. So of course they have to be quantitative variables. Now how can I talk about quantitative variables in terms of correlation analysis? So we'll start with something called a bivariate analysis. A bivariate analysis is essentially an analysis considering just two variables. So you have bi, which is two, and variate, which refers to variables. So we'll be starting with bivariate analysis. Now we know of the Cartesian system, that is the xy plane, and we can represent two variables on the xy plane. So we can have a vertical axis and we can have a horizontal axis. Let me just change the axis just a moment so that I can talk about it in greater details. If it's in block, then if it's in dot, then it will be difficult to interpret. Okay, so let's say I have these two axes. So I have a variable y over here and I have a variable x over here. In our previous episodes or in our previous lectures, we have talked about them in terms of points in two-dimensional space, or an alternative representation was the representation of complex numbers in this plane, in the Argand plane. When we talk about complex numbers, here we will be talking about two different variables, x and y, and we'll be trying to understand the relationship between them. So what do I mean by trying to understand the relationship between two variables? Suppose I have two variables. So let's say I have the relationship between one variable x is, let's say, the rainfall of a particular place. So let me change the color. So let's say I want to look at the rainfall of a particular place, and suppose I want to look at the agricultural output of that particular place. So I want to look at rainfall and I want to look at agricultural output. Now we know that agricultural output is heavily dependent on rainfall. So specifically in India, it's a very rain-based, temperature-based agriculture system. In India is very temperature-based and it's very climate-based. So if there is low rainfall, agricultural output can be expected to be low. And if there is sufficient rainfall, I wouldn't say high, but if there is sufficient rainfall, I would expect agricultural output to be high. So I am assuming that x stands for rainfall and y stands for agricultural output. Now the agricultural output increases in this direction and rainfall increases in this direction. So suppose if I have a low amount of rainfall, I could expect a low amount of agricultural output. Comparatively, if I have a higher amount of rainfall, I would expect a higher amount of agricultural output. Now in order to understand the data, this is my theoretical concept. I would expect this to happen. But what actually happens? I need data, right? So I might be able to collect data. Suppose I want to collect data of the past 50 years. and I collect data every year about the total or maybe average annual rainfall of India for the past 50 years, and I take the average agricultural output of India for the past 50 years. So essentially what you will have is 1 year, suppose rainfall was this much and agricultural output was this much. Suppose in 1 year rainfall was this much, agricultural output was this much. Suppose in again another year rainfall was this much, agricultural output was this much. All these points will represent 1 year. So we have 50 years to consider. So there will be essentially 50 such points in our graph. Now of course some of these points can lie here, some of these points can lie here, some of these points can lie here, but we could expect that these points would more or less lie somewhat in this manner. So it will be like this, right? Now what happens is, what statisticians found out is, we can look at the way this data is arranged in this two-dimensional space. Now this diagram, it's essentially a scatter of, like, the data points are scattered around the place, right? So this diagram is called the scatter plot. So this diagram, let me just write that down. This diagram is called a scatter plot. What it does is it points the different data, the data points in a two-dimensional set, and it allows you to look at the data that you have collected pictographically, and that allows you to give you a very basic and a preliminary idea of how your data behaves. So as I can see from my data, there is sort of a positive relationship between rainfall and agricultural output. That is, if one increases, the other can be expected to increase. But of course, it doesn't increase just like that. It's not a strict positive relation. There might be other instances, because reality cannot be captured as easily as I would expect hypothetically. But in general, I can see a positive relationship. Now, how do I can see this graphically, but how do I mathematically represent it? What statisticians did is they divided this two-dimensional plane, they divided it into 4 parts. So I have a vertical axis and I have a horizontal axis. They divided it into 4 parts. Now, why did they divide it into 4 parts? What they did is, if you look at the 4 parts, suppose I shift, this was the initial origin that I had considered, the origin for the x-axis and the origin for the y-axis. Suppose I shift this origin to this point. That means this becomes my new axis x prime and this becomes my new axis y prime, right? I can do that from coordinate geometry. I know that I can shift those points from here to here. So I'll have a changed origin, and I'll basically let us consider the same scale. So I'll have a change of origin. I'll discuss about how to mathematically change the origin in a different video, but that is just pure mathematics. That's not anything statistical as such. Now what that does is, essentially what you had was only positive values of x and positive values of y. Now that you have changed the origin of your data set, essentially what you do is, this point represents the average of x's. So if you have different amount of x's, so you have this value of x, 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 so you have different values of x over the x-axis, right? What you do is, you take the average of all those x's and you mark x bar over here. So you mark x bar, that is the average rainfall for the past 50 years. That is the average annual rainfall for the past 50 years of India, the data among the data that you have collected. Similarly, you find out the average agricultural output for India for the past 50 years from the data that you have collected, and you get some y bars. So essentially there was a agricultural output like this, there was an agricultural output like this, there was an agricultural output like this, and you take up the average of all of these values and you find a y bar. And then you draw a horizontal axis across y bar and a vertical axis across x bar. What that does is, it shifts this data, the origin of the data set, to the point x bar comma y bar. So this point essentially is x bar comma y bar. That is simple to understand. So we have the shifted origin to x bar comma y bar. Now what happens is, the value of all these points change. Essentially all these points represented positive value, right? All of these points were positive with respect to this origin. But when we talk about this origin, these points are actually in the third quadrant. So this is the first quadrant, this is the second quadrant, this is the third quadrant. So this quadrant that I'm talking about, this is the third quadrant, and this is the fourth quadrant, right? So essentially what happens is, these values, they turn out to be in the first quadrant. These values, there are 2 values which turn out to be in the second quadrant. There are about 1, 2, 3, 4, 5 values which turn out to be in the third quadrant, and about 3 values turn out to be in the fourth quadrant. Now what happens is, as you can see, since I had predicted that there will be a positive relationship between rainfall and agricultural output, since positive relationship means I can expect a straight line like this, there are more values in the first quadrant and in the third quadrant. There are hardly any values in the second quadrant.